First thing we're going to look at in this video is this concept of, well, if I'm in a particular situation, what is the set that sort of contains everything that I'm considering to be possible elements? So that set of everything we're considering to be possible elements of our sets is called the universal set. So what is your universe, if you will? It has a notation. It's denoted with a big capital script U. So this is a script U. And sometimes an example helps when we're thinking about this. So maybe you're talking about situations where I'm talking about sets where everything I'm considering are all positive whole numbers. So then my universal set would be the counting numbers. A somewhat more world example would be something like this. If we're discussing sets of students in particular classes at Sterling College. So for instance, a set might be all of you guys who are enrolled in contemporary math right now. You can make a set that contains all of your names. If I'm doing that for multiple classes at Sterling, then my universal set, well, it would be all students currently enrolled at Sterling College. So let's practice writing that in set builder notation. So it would be the set containing all x, such that x is a student currently enrolled at Sterling College. Right, anyone who's going to be on one of those class lists needs to be an element of this list. So, for instance, all of you would be elements of this universal set, but someone like my mom would not be an element of this universal set. This list, the list of all students currently enrolled at Sterling College, would be like the list that the registrar has, right? They have every student, and then we can make subsets of those students who are then enrolled in particular classes at Sterling. So it's just a useful tool to use. Sometimes we can, based on an example, interpret what our universal set is. And sometimes in an example, we'll just define what the universal set is, and we'll just use the defined one. So one of the things we're going to do next, somewhat using this idea of universal sets, but then going back to that idea of subsets that we just learned, is how can we find all of the subsets of a set? So let's try an example. Let's list all of the subsets of U, so a universal set that contains the numbers 1, 2, and 3. So we'll start with a fairly simple example. Now, we need to list every set that is a subset of this. We could just start to kind of take a stab at it. So we might think about things like, well, I could just take the set containing 1. Or similarly, I could just take the set containing 2. Or similarly, I could just take the set containing 3, right? Those are 3 examples of subsets, but they're not all of them. So one thing that I find helpful is to write down the subsets using a system for defining how to determine which subsets I'm looking for. So what's in common with all of these subsets? Well, they all contain one element. So these ones contain one element. So instead we could contain 2 elements. So that could be something like, we'll pick two of the things from up there. So I could have the set containing 1 and 2. I could have the set containing 1 and 3. Or I could have the set containing 2 and 3. But then remember, there are still more options. Now, I didn't start with it in this one, but normally I would start with it because he's a tricky one to remember. Remember, you can always pick no elements. What's the set that contains no elements? It's the empty set. So remember, that was our fact. The empty set is always a subset of every set. So this will always be on your list. And if you're listing it in this way, 0 elements would come first. So 0 elements, then 1 element, then 2 elements. We still have another option. I could pick all 3 elements. And if we think about it, there's only one way to do that. I have to take the 1, I have to take the 2, and I have to take the 3. Now, if we think about it, there's no way to pick less than 0 elements. And I also, in this example, can't pick something with, say, 4 elements because there just aren't that many to pick from. Remember as well, when we're writing down sets, be careful that you're writing them properly. So I've written all of these in roster method. They're in curly braces, and things are separated by commas, right? If I just put a curly brace with a 1, 2, and curly brace, that looks like the set containing 12, which is not the same thing. But also remember that rearranging elements is not a new set. So I would not say write down the set containing 3, 1, and 2, because it's not new, it's just something that I've already written already. So these would be the only unique subsets. And these are all of the subsets. Now notice, we could have asked a slightly different question to say, well, which ones are proper subsets? Well, if we think back to our definition of a proper subset, it was a subset that was not equal to the original set. So, if we're looking at this list, there's only one on here that doesn't count as a proper subset. So note all of these except the one that's equal. The set containing 1, 2, and 3 are the proper subsets. So the empty set, the set containing 1, the set containing 2, the set containing 3, the one with 1, 2, the set containing 1, 3, and the set containing 2, 3. If we were asked to list the proper subsets, we would list all of those and just not the one that has everything in it. So not the one that's equal. It's the only one that's not proper. Everything else is. We could do this with other examples of sets. We could do it with more elements in our set. It would just take a little more time. But again, we could kind of be fairly systematic and be careful to check that we have everything. Now, a helpful question that could either help us list everything, or there's a chance that maybe I don't care what the list is, but just how many of them are there. This fact then can come in handy. So, like if we look at this example, notice we found 1, 2, 3, 4, 5, 6, 7, 8 subsets of the set containing 1, 2, and 3. Our fact is going to tell us how many subsets a given set has, and it's dependent on how many elements it had. So if there are n elements in a set, then that set has 2 raised to the power of n subsets. 2 to the power of n, so that's an exponent. So that makes sense. In our example up above, n was 3, and 2 to the power of 3 is 8. So we did find 8 subsets. So we found them all. Now another question we might ask is how many proper subsets does it have? So it has 2 to the n subsets and some number of proper subsets. Well, when we looked at our example up above, almost everything was a proper subset except the one that was equal. That would have been the same even if my list was bigger, right? A proper subset is just a subset that's not equal. So it's going to be, start with that 2 to the power of n, and then get rid of one of them. So from that total, subtract 1. So like up top, we would take 2 to the power of 3, which is 8, and then take away 1 from 8. There are 7 proper subsets, the first 7 that we listed. Let's try an example where all we want to know is the number of subsets. So in this example, how many subsets are there of the set containing pepperoni, onions, peppers, and olives? So probably this is like a pizza menu, right? And these would be options of toppings that we can put on our pizza. So really we're asking how many different pizzas are possible with these toppings. Now, we're going to not list them all, because notice it doesn't matter. It doesn't say list them. It just asks how many. So we're going to use our formula. So there are how many elements and if we count them, right, there's pepperoni, onions, peppers, olives, there's 4. So n here is 4. So we would have 2 to the power of 4, which is 2 times 2 times 2 times 2, which is 16 subsets. So 16 subsets, 16 possible pizzas with these different toppings. So one of them is like the pizza that only has pepperoni. One of them just has peppers and onions. One of them has none of the toppings. It's a plain pizza. One of them has all 4 of the toppings. It's like the everything pizza. Now we could ask how many proper subsets we would take a look at. Well, again, there are 4 subsets, so it would be 2 to the 4th, and then minus 1, so it's 16 minus 1, there's only 15 proper subsets. Notice it's everything, it's all of these ones, it's the same list, except not the one that contains everything, not the pepperoni, onions, peppers, olives, pizza. So what we're going to do next is we're going to work on our worksheet for 2.1 again. You've got kind of a long question for the next one that puts together a lot of different ideas and helps us think about some of these concepts. So it's asking about Again, it's like a toppings question. Again, try it on your own. If you're having trouble working on it, definitely jump on to the next video and look at some pieces of the video to get you moving in the right direction. And then when you're done working on the question, look at the full solution to that video.